At the end of the previous lecture, we started discussing linear transformations and linear transformations of a finite dimensional vector space V. We showed the connection between such linear transformations and ring theory by the means of evaluation map. So I give you a polynomial with coefficients in the field F. And then you essentially evaluate this polynomial at T to get an endomorphism of the linear transformation. Notice that the endomorphisms of a finite dimensional vector space can be identified with n by n matrices with entries inside the field F by means of choosing a basis for the vector space. So essentially, we are giving a ring homomorphism from the ring of binomials to n by n matrices with entries inside F. This ring homomorphism is also F linear, so we are giving an F linear homomorphism from F bracket X to MNF. Essentially, I give you a polynomial, you evaluate it at this matrix that's given by the linear transformation T. We use this in order to define the minimal polynomial of a linear transformation. Now, we also formulated this important question that when I give you a linear transformation, how can we encode this linear transformation in terms of matrices? We discussed that having a basis, we can always find this matrix associated to this linear transformation, and we can ask for the best choice among all the matrix representations for this linear transformation. And one way of saying what best refers to is by sparsity of the matrix that represents this linear transformation. So if we have more zeros, then it's easier to do the computation, to do the needed computations with the matrix. And at the same time, it can give us a better insight in how this linear transformation actually acts on the vector space. So our goal is to find sparse matrix representation for the linear transformation T. We also interpreted this in terms of matrices and said, if I give you a matrix A, we are essentially looking for a conjugate of A that is sparse, that has many zeros in it. Now, we pointed out the key ingredient and the key point of view that's going to help us to answer this question. We said that we can view this finite dimensional vector space V as an F bracket X module. So F bracket X acts on this vector space, so to speak. So we can view V as an F bracket X module with the following scalar multiplication. So given a polynomial F and a vector V in the vector space, we define F dot V to be what the matrix or endomorphism after evaluating F at T does to the vector V. So essentially F dot V is nothing but phi sub T evaluation at T of F times or applied to the vector V. So when I say times, it's the point of view when we take a matrix, a basis for the vector space, and we view endomorphisms as matrices, then this is essentially multiplication of matrices. Or when we take the point of view of endomorphisms, it's better to say that we are applying this endomorphism to V. And it is actually rather easy to check that it does satisfy all the properties of a scalar multiplication of modules, and that means V is an Fx module. Now, because V is a finite dimension, if I pick a basis, an F basis, then every vector inside V is an F linear combination of these vectors. And notice that if I give you a scalar polynomial, just an element inside F, then C times, so for every C inside the field, if I think about it as a subfield of ring of polynomials as the constant polynomial, then C dot V is compatible with CV, all the scalar multiplication of the vector space capital V. So that means if I tell you V1, V2, Vn, the F span of Vi's give me the entire vector space capital V, we can deduce that Vi's also generate V as an F bracket X module. Knowing that dimension of V as an F vector space is finite, we can deduce that it is a finitely generated F bracket X module. So altogether, we have used this linear transformation T to view this finite dimensional vector space as an Fx module which is finitely generated. Now, F bracket X is a Euclidean domain. This we have proved long ago using long division. Now, this is a Euclidean domain, and V is a finitely generated module over this Euclidean domain. So I can use the classification of finitely generated modules over Euclidean domains. Using that classification, we can deduce that there is some non-negative integer k and vectors d sub I and polynomials d sub i's, d sub 1, d sub 2, so on, so that each one divides the next one, and my vector space, which is an fx module, a finitely generated fx module, as an fx module is isomorphic to fx raised to power k times fx mod out by the ideal generated by d1, fx mod out by the ideal generated by d2, fx mod out by the ideal generated by d sub r. So this isomorphism is an fx module isomorphism. Now notice that when something is an fx module isomorphism, because the scalar multiplication of fx is compatible with the scalar multiplication of f, as we have discussed over here, let's say, it is also an f linear map. So this isomorphism is also an isomorphism for vector spaces. In particular, both sides should have the same dimension over f. Now, the left-hand side, V, is a finite dimensional vector space over F. So the right-hand side should be also a finite dimensional vector space over F. That would imply that Fx raised to power k should be a finite dimensional vector space over F. But ring of polynomials is of infinite dimension over F. So that implies that k should be 0. There should not be a component consists of f bracket x. So altogether we deduce that this vector space V as an fx module is, so and dimension of this guy is infinite, not 0. We deduce that the power is 0, so we deduce that V as an vector as an fx module is isomorphic to the quotient of fx by the ideals generated by d1, d2, and so on. Notice that if di's are constant polynomials, non-zero constant polynomials, we can we get a zero factor and we can get rid of it. So that means I can assume without loss of generality that d sub i's are not non-zero constants. And they cannot be 0 as well. I mean, we have already pointed this out, that d sub i's are non-zero elements of f bracket x that came out of classification. So far we have these non-zero, non-constant polynomials, d sub i's, each one dividing the next one. And moreover, because only the ideal generated by these are important, I can multiply by the inverse of the leading coefficient and assume that they are monic polynomials. So altogether, we are getting monic non-constant polynomials, d1, d2, dr, each one dividing the next one, and my vector space is isomorphic to the Cartesian product of these quotient modules as an fx module. Okay, so let's call the isomorphism something. So suppose this theta is an fx module isomorphism from this Cartesian product to V. How does this help us to understand the linear operation T? So that's the key. I mean, we started with this linear operator T. We want to understand this, and then we introduced this modular structure on V that uses this linear transformation T. And now we have a fairly good understanding of the modular structure. We go back to the linear transformation and try to see what we can say about it. So let's, for brevity, so let's look at let's call the left-hand side to be M. So M is this fx module. It can be also viewed as a ring, but here we are thinking about it as an fx module. And because this theta, is an fx module isomorphism, we have that, so this M is an fx. So then here I didn't mean to write this down. Let's erase this. Now, because because theta is an fx module isomorphism, for every m that I give you inside this right-hand side, in the left-hand side, capital M, this theta applied to x dot m should give us x dot theta of m. What does that mean? This means that this the following diagram is indeed a commutative diagram. So what is this diagram? If I start with m and multiply by x, so I'm going to denote it by this x times. So if I multiply by x and go to m, so it's like this, I get m multiplied by x, and then apply theta, I end up getting x times theta of m, because theta is an fx module homomorphism. But x dot theta of m, by definition, is theta applied to theta, t applied to theta of m. Remember, whatever polynomial I give you, you have to evaluate it at t, you have to substitute t for x, and then apply it. That's what we are doing. So that means that I can first apply theta and go down to v, and then apply t. So these two are going to give us the same value. That means that this diagram is a commutative diagram. So this is one way of thinking about it. Now, you see, because this theta is an isomorphism, and this shape is a commutative diagram, that means that if I find a basis for this linear transformation, multiplication by x, I can simply write the same matrix for the linear transformation V, because they are essentially the same things. I can replace m by v and replace multiplication by x with t, and I'm getting the same transformation. So that's how this fx module structure is going to help us. But because now all of a sudden I have this concrete fx module, and we have this concrete transformation of multiplication by x. And for this particular linear transformation, I'm looking for a sparse matrix representation. Okay, so let's see how this can help us. So now our goal is to find a nice matrix representation for multiplication by x on this module. Now, notice this module itself has R copies, R submodules, R factors that are giving us the entire module. So let's call the ith copy, ith factor, m sub I. And because I want to think about it as a submodule of m, I'm going to include 0 components in the other factors. So I put 0 components everywhere except the ith factor, and there I allow the entire factor and call that guy m sub I. Notice that when I add m sub i's, I get the entire m. So m is nothing but summation of m sub i's. And also notice that if I give you vectors from different m sub i's, they are f linearly independent. Because every factor that one of them has, every non-zero component that one of them has, the other ones have 0 in those components. So that means that if I tell you that a linear combination of them is 0, then all the coefficients are 0. Okay, so we get these subsets of M. They add up to the entire M, and they are linearly independent. That means what? That means if I choose a basis for M1, choose a basis for M2, choose a basis for the dot till M sub R, after putting them together, I get an ordered basis for the entire M. So again, because, okay, so if I want to show that they form a basis for the entire M, I need to show why they span the entire M and why they are linearly independent. Notice that because B sub i's span M sub I, span of B contains all the M sub i's, and M sub i's add up to the entire M. So that's why the span of the right-hand side is the entire M. Now, why are they linearly independent? I pick a linear combination. Now, this linear combination, if I collect them, I get linear combination of this part gives me an element inside M1, linear combination of these parts give me an element inside M2, and so on. But when I add a bunch of elements inside M sub i's, if I end up getting 0, then all of them are 0. Remember, the M sub I has a non-zero component only at the ith factor and only at the ith component. So if they add up to 0, then all the components are 0, implies that the linear combination of B sub 1, the linear combination of B sub 2 parts are 0. Now, knowing that they are linearly independent, we deduce that this set B is indeed a basis for the entire M. Now, if I write down multiplication by x in this basis, let's see what we get. Notice that when I multiply by x, these M sub i's go to each other, go to themselves. They are submodules of M. So when I multiply by x, I send a vector inside M sub I to a vector inside M sub I. If I start with B sub 1 and multiply by x, I will be in the span of vectors inside B sub 1. So there will be no components, no non-zero coefficients in other parts. Only I need to understand how to write down the matrix representation of multiplication by x when I restrict it to M1. So this is multiplication by x inside f bracket x mod out by d1. Then it's multiplication by x in f bracket x mod out by d2. Multiplication by x in fx mod out by the ideal generated by d sub r. And the key point is that now I have this block form for my matrix, and everything except the diagonal blocks are going to be 0 because M sub i's are invariant under multiplication by x. So when I multiply something inside M sub I, when I multiply some element of M sub I by x, I end up getting another element of M sub I. That means that when I start with a vector inside the base b sub I, after multiplying by x, I get a vector that's a linear combination of vectors inside b sub I. In particular, the coefficient of this linear combination, the coefficients of this linear combination, the only possible non-zero ones are the ones that are inside b sub I, and the other ones will be 0, which means that I am going to get this kind of block form for my multiplication by x. That's fairly sparse. Now we want to go further and look at this, the blocks. For all we know, r might be 1, then I have only one block. So the question is, can I find a nice basis for the module that's given by fx modeled by a monic non-constant polynomial d? So I give you a monic non-constant polynomial, so that means a polynomial of this form, x to the m plus a sub m minus 1 x to power m minus 1 plus dot plus a sub 0. I look at the quotient ring, think about it as an fx module. Then here I look at the operator that's multiplication by x, that's linear operator. And I'm asking if I can find a sparse matrix representation for this linear transformation. Okay, but this kind of quotient, we have already seen a basis for it. We know that the dimension of this guy is precisely the degree of the generator of the denominator. And the way that we proved it was using long division and the fact that the remainder is unique. So every element in this quotient, in this coset, every coset representative can be replaced by the remainder of that coset representative divided by d, which means every element here can be represented in a unique way as a linear combination of 1 bar, x bar to the power m minus 1, and these bars means that I'm looking at the coset that they represent. So by using long division, we deduce that every element in this quotient can be written in a unique way as an f-linear combination of these vectors, which means that this ordered set of elements form an f basis for this space. Now, we have an f basis. Let's find out what is the matrix representation of multiplication by x with respect to this basis. So I'm given a linear transformation. I want to find out what the matrix representation of this guy is. The rule is that I need to apply this linear transformation to elements of my basis, and I have to write it down as a linear combination of the elements of my basis and write down the coefficients in the jth column. So when I apply this linear transformation to the jth element of this basis, whatever coefficients I get, I have to write them in the jth column. Putting together all these vectors, we end up getting the matrix representation of multiplication by x in this basis. So I need to apply multiplication by x to the first element of the basis. As I multiply this by x, I get the next one. That means, okay, now I need to write this as a linear combination of these elements, but it's clear that it has only one of them. This means 0 coefficient of the first one, 1 times the second one, 0 times the third one, 0 times the rest. So I get one of the standard bases, e sub 2. That means the first column of the matrix representation of multiplication by x is e sub 2. Now I apply multiplication by x this time to the next vector, which happens to be over here. When I apply to this, I get x squared bar. Again, in this basis, it's nothing but e sub 2. The way that you write this down as a linear combination of these vectors, these elements, is letting 0 for the first element, So the first one times 0, the second one times 0, the third one times 1, and 0 times the rest. That's E sub 2. So the matrix representation of this is just E sub 2. So the second column for multiplication by x would be E sub 2. And we repeat this till we reach to x to power m minus 1. Now story is different. When I multiply this guy by x, I get x to power m, which is not here. So I need to write down x to power m as an f linear combination of these elements. Now, what is x to power m in terms of these vectors? Now, again, when we multiply this, we get x to power m. But what is it? We are looking at the quotient of f bracket x by d. And the general rule is that we need to divide by d and find what the remainder is. And that would be the way that we can write it down in terms of a linear combination of 1 bar, 2 bar, dot x to power m minus 1 bar. In this case, actually, division is rather easy. The quotient would be 1, and then we subtract. We end up getting the rest. I mean, this would be our leading coefficient of t, leading term of d, and then we subtract the rest. So clearly, when I look at it mod d, that's d, this is the polynomial that we have. So this polynomial, which is d, mod d, of course, it's 0. Now I can let this guy on one side and bring the other ones to the other side and get this equality. This means when I write this down as an f linear combination of 1 bar, 2 bar, dot x to power m minus 1 bar, the coefficient of 1 bar would be negative a sub 0. That's over here. The coefficient of x bar would be negative a sub 1. That's over here. And we continue like that till we get the coefficient of x to power m minus 1, which is negative a sub m minus 1. So as you can see, when we apply to 1 bar, we get x bar. So that's the coefficient for x bar, and the other coefficients are 0. When I apply it to x bar, I get x bar squared. That's the coefficient for x bar squared, and the other coefficients are 0. And we continue like that, having ones just below the diagonal till we reach to the last column. There, we have to put negative of all the coefficients of the polynomial d. So as we can see, this is a fairly sparse matrix. It's completely easy to be written down in terms of the polynomial d. So I give you the polynomial, you can easily write down this matrix, and this matrix is called the companion matrix of the polynomial d. And we write it as C of d. So C of d is this matrix, and it's called the companion of the polynomial d. So altogether, we deduce that, so if I go back over here, we started with this vector space. Then we said this vector space can be identified with this M. And via this identification, the linear transformation T can be identified with multiplication by X. Then we used these submodules and said the matrix form of multiplication by X is this block form of matrix forms of multiplication by X for these smaller rings that are of the form f bracket x mod out by some monic non-constant binomial. And for these ones, we found a basis that's of this form, where the matrix form of multiplication by X is nothing but the companion matrix of D. So that means I have to put here the companion matrix of D1, put here the companion matrix of D sub 2, the companion matrix of D sub R. So that's a fairly sparse matrix, and it gives us a fairly good understanding of how this linear transformation works. Now, let's also point out what the minimal polynomial of this multiplication by X is, at least when I'm working with this easy vector space or module f bracket X over the ideal generated by D. So if I apply the evaluation, so how did we define the minimal binomial? It means I have to apply evaluation map to a binomial, and I ask myself, what is the kernel of this map? So when I apply evaluation at some binomial, what does that do? So whatever binomial f I give you, you are supposed to evaluate it at multiplication by x. So this means we have to do what? We have to do the following. I give you a binomial f, you plug in x multiplication, and then you feed it some vector. And that's supposed to be, so if f has coefficient c sub I, it's supposed to be c sub I x multiplication I times v. But as you can see, this is the same as saying that I take c sub I x to power I and then multiply it by v because of the distribution property. So that means that evaluating binomial f, substituting multiplication by x into f, it's the same as multiplying the binomial f of x by the module. So this is going to be 0 if and only if multiplication by f, multiplication by x from this module to itself sends everything to 0. In particular, multiplication by f is supposed to send the constant function 1 to something 0, but that means that this is supposed to be 0. So again, if I tell you that f is in the kernel of evaluating at x, that implies that this should be the 0 coset, which is the same as saying that f should be a multiple of d. And conversely, if f is a multiple of d, then when I multiply it by any coset, the coset representative would belong to this ideal. And therefore, the coset representative is 0. So what we showed, if I summarize it, what we showed is that the kernel of evaluation at multiplication by x is nothing but the ideal generated by d. So here I'm thinking about multiplication by x from the module f bracket x modeled by the ideal generated by d to the module, to the same module. So altogether we deduced that a binomial is sent to 0 under the evaluation map if and only if it is a multiple of d. That means, knowing that d is a monic binomial, that means that the minimal binomial of this linear transformation is nothing but the companion of d. So altogether, we have two results now that I'm going to summarize it in the following theorem, that if V is a finite dimensional F vector space, then T has a matrix representation with respect to some basis. It looks like this: companion of a binomial D1, companion matrix of binomial D2, companion matrix of binomial D sub R. For some non-constant monic binomials, each one dividing the next one, and moreover, the last one is the minimal binomial of T. Okay, let's see how the proof goes. We have proved more or less the entire statement, maybe except the last part, why D sub R is the minimal binomial of T. But before I go to the proof, let me emphasize that, okay, so this form is called a rational canonical form of the linear transformation T. One can show that this form is indeed unique, but we are not going to show it right now. So we just discuss the existence part. So this theorem implies the existence of a rational canonical form for a linear transformation from a vector space f to the n to a vector space f to the n. Let's summarize what we have already discussed and complete the proof. What we did was we started with this V and thought about it as a finitely generated fx module. And then what was the scalar multiplication? The scalar multiplication came from evaluating a polynomial at t and then applying it to the vector v. It's clear that it's a finitely generated fx module, and in the used classification of finitely generated modules over a Euclidean domain. We noticed that f bracket x is a Euclidean domain, so we are allowed to use it. Combine it with the fact that dimension of V is finite as an f vector space. Deduce that V as an fx module is isomorphic to fx over the ideal generated by D1, fx mod out by the ideal generated by D2, and so on. For some, we used a bit of ring theory and said for some monic non-constant polynomials, D1 dividing D2 dividing dr in f bracket x. So because a bit of discussion, the ideal doesn't change as I change it up to a unit, so I can assume that d sub i's are monic. I can drop the zero factors, so I can assume that they are non-constant. So d sub i's are non-constant monic polynomials. Now, because the left hand, we call the right hand side M. Now we have this isomorphism, and this isomorphism sends the multiplication by x to application by t. So this means that applying t is the same as multiplication by x when I change the copy of v to m using theta. So instead of finding a matrix representation for t, we are going to find a matrix representation for multiplication by x. Multiplication by x preserves these factors, and these factors generate m, and they are linearly independent. So that means if I find a nice basis for these factors, I can put them together, get a basis for the entire m, and then in that basis, multiplication by x looks like these diagonal block forms. So that means I need to discuss these blocks and what kind of shape they are. We pick a basis for these quotients, and these ones are coming from long division, and they are essentially 1 bar. X bar the cosets that are represented by 1 x to the dot x to the power m minus 1, where m is degree of t. Then we discussed that the matrix of multiplication by x is nothing but the companion matrix of the monic polynomial d. Moreover, we showed that the minimal polynomial of this map from f bracket x mod out by d to f bracket x mod out by d is also the d itself. So these are the things that we discussed. But now remember that if I put these blocks over here, we get this block form. That's exactly what we wanted to get to. So we showed the existence of a rational canonical form. And now let's discuss why d sub r is the minimal polynomial of this operator. Notice that when I evaluate a polynomial at this matrix, because this matrix is of block forms, when I square it, I need to only square the blocks. When I raise it to power 3, I need to raise the block diagonal blocks to power 3, and so on. That means that when I want to evaluate a polynomial at this matrix, I only need to evaluate these polynomial at the blocks and then put them on the diagonal of this matrix. Knowing that this f evaluates to 0 at this matrix, we deduce that this happens precisely when all these diagonal entries are 0. So f evaluated at this matrix is 0 if and only if each one of these companion matrices evaluated at f, f evaluated at every one of these companion matrices should be 0. But that means the minimal polynomial of these companion matrices should divide F. And these companion matrices are matrix representations of X times multiplication by X in this ring. And we discussed that the minimal polynomial of this guy is just dx, the polynomial d. That means that the minimal polynomial of the companion matrix of d sub I is d sub I. Knowing that F is supposed to be 0 after evaluating at this matrix, we deduce that d sub i's should divide F. So altogether we get that F evaluated at this matrix is 0 precisely when d sub I divides the polynomial for every I. But because d sub 1 divides d sub 2, d sub 2 divides d sub 3, and so on, then this holds precisely when d sub r divides F. Because this is an infinite leaf and d sub r is a monic polynomial, we deduce that the minimal polynomial of this matrix that is of the block form is d sub r, and that's exactly what we wanted to show. Because we know that the minimal polynomial of the linear transformation is the same as the minimal polynomial multiplication by X, and that one is the same as the minimal polynomial of the matrix representing that guy. So we get that the minimal polynomial of T is d sub r. So let's look at it again because it's extremely important. Look at the statement. Whatever linear transformation I give you, you can always find monic non-constant polynomials d1 dot dr, each one dividing the next one. And my linear transformation, our linear transformation, has a matrix representation of the following form. A block matrix. On the diagonals, we have companion matrices of d sub i's. And moreover, the d sub r, the last one, is the minimal polynomial of the entire T. So the minimal polynomial of T is d sub r. So the last one, at least we have a complete understanding of. It's precisely the minimal polynomial of the operator T. Now, we have also seen what determinant is in your homework assignment. You have seen it for every arbitrary unitary commutative ring. We can apply it to the ring of polynomials and define determinant of xi minus a. We end up getting an element of R bracket x, and we call that guy the characteristic polynomial of this matrix. So we can do it for an arbitrary unital commutative ring. We are going to use it when R is a field. So that way we can define the characteristic polynomial of a matrix with entries inside a ring or a field, unital commutative rings. Now, next I want to define characteristic polynomial of a linear transformation over a finite dimensional vector space. So suppose V is a finite dimensional F vector space. Then T from V to V, and suppose T is also an F linear map from this finite dimensional space to itself. I want to define determinant of T. We have, I want to define not only determinant of T, but also a characteristic function of T. We have defined it at the level of matrices. Now let's see how far we can go at the level of linear transformations. So we have learned that we can attach a matrix to a linear transformation by choosing a basis. So let's choose a basis. And let's look at the matrix that's represented by the matrix representation of T with respect to this basis. Now I can talk about determinant of T and characteristic polynomial of T using this base B. So I call this guy to be the characteristic polynomial of T. So the characteristic polynomial of the matrix representation of T in the base B, I'm going to call it to be the characteristic polynomial of T. And determinant of this matrix, I'm going to call it to be determinant of T. A priori, these definitions depend on the choice of B. Next, we are going to show that these are in fact independent of the choice of B, and therefore they just depend on the linear transformation. So it is okay to call them the characteristic polynomial of T and the determinant of T, rather than saying the characteristic polynomial of T comma B and the determinant of T comma B. So let's see why these values, these quantities are independent of the choice of B. Remember that if I choose two different bases, then the matrix representations are conjugate of each other. So if we show determinant and characteristic functions, characteristic polynomials do not change after conjugation, we get the desired result. So suppose A prime is a conjugate of A. That means A prime is S inverse, where A is some n by n matrix and S is invertible. Here we don't need to work with fields. We can work with an arbitrary unital commutative ring R. In that setting, I want to say that determinant of A prime is determinant of A. So determinant doesn't change after conjugation. And the characteristic polynomial of A prime is the same as the characteristic polynomial of A. Characteristic polynomial doesn't change after conjugation. Using this, we can deduce that if I start with a linear transformation from a finite dimensional vector space to itself, if I choose two different bases of this vector space, the characteristic polynomials that we get after looking at these two different matrix representations of T are going to be the same. So the characteristic polynomial of this linear transformation does not depend on a choice of a basis. So it just depends on the linear transformation. The same is true for determinant. Okay, let's see why this is the case. So we have already discussed, and you've seen it in your homework assignment, that determinant can be defined at the level of rings, and determinant is multiplicative. So determinant of xy is determinant of x times determinant of y. In particular, determinant is a group homomorphism from invertible matrices to units of the ring R. So let's see it in a concrete way. Determinant of S times determinant of S inverse is determinant of S times S inverse, which is the identity matrix, and determinant of identity matrix is 1. That means determinant of S is a unit and its inverse is determinant of S inverse. Or I can say determinant of S inverse is inverse of determinant of S. Therefore, determinant of A prime, which is determinant of S, A, S inverse, but determinant is multiplicative, so that would be determinant of S times determinant of A times determinant of S inverse. But determinant of S inverse is inverse of determinant of S, and R is a commutative ring, so I can put it closer to determinant of S. We get this equality. These guys cancel out, and we get determinant of A. As we can see, that if I give you two conjugate, say if I conjugate a matrix, determinant doesn't change. Now I'm going to use this to show the characteristic polynomial of a matrix doesn't change after conjugation. So I give you a matrix A and I conjugate it. I want to understand characteristic polynomial of A prime. That means I have to look at the matrix xi minus A prime and look at its determinant. Xi minus A prime is xi minus SAS prime. Now, I can factor out S and S prime from both sides. And this is the same as S times xi minus a S inverse. You see, when I use the distribution property, I need to multiply x and S and S inverse from both sides, but then S xi S inverse is simply xi. Multiplication by a scalar matrix is in the center. I can pull it out, and then S times S inverse is identity. So the first factor would be just xi, and the second factor is simply conjugate of a by S. Now that means that xi minus a prime itself is a conjugate of xi minus a in mn r bracket x. Therefore, determinant of this matrix is the same as determinant of this one. Determinant of xi minus a prime is the characteristic polynomial of a prime, and determinant of xi minus a is the characteristic polynomial of a. So we get that these two are the same as we wanted to show. Now, when I give you two different bases, as we discussed, the matrix representations are conjugate of each other, so they end up having the same characteristic polynomials, and that would give us the second part of this lemma. So I can talk about characteristic polynomial of a linear transformation. Now, it is also useful to look at this intuitive equality, and I leave it as an exercise. You will prove it in your homework assignment. The determinant of a matrix that is of block form A1, A2, Am is product of determinants of the blocks. So if you think about it in terms of the definition of determinant, we have this summation over all the permutations, and then we take these permutations and look at the corresponding entries of the matrix and multiply them, add them up in terms of the sign of the permutation. Now, if I give you a permutation and this permutation has entries over here, so if these sigma i's do not send the blocks of A1 to themselves and blocks of A sub 2 to themselves and so on, then the corresponding term in the summation would end up being 0. So this means only those permutations are allowed that send the interval attached to the block of A1 to itself, the interval attached to the block of A2 to itself, and so on. So every permutation that I give you, it would be composition of permutations attached to intervals for the block A1, for the block A2, and so on. So from there, we can say that we can deduce that only these, we can write down the whole summation as a product of summations where sigma I varies among the permutations for the block A1 and so on. And we notice that sign of the product of these permutations would be the product of the signs. So altogether, you get the equality that we are looking for. So what I'm suggesting for this exercise is you write down these determinants, you write down the definition of determinant in terms of the summation of over all the permutations of the attached blocks, the indices of the blocks, distribute all these summations, and argue that only those summations appear in the side, and the other extra terms that we have here, all of them are 0, because simply we have 0 entries in the product attached to a permutation that doesn't send these blocks to themselves. That's the outline of the proof of this exercise, so I leave it for you to complete the details. Now, using this, we end up getting the following important proposition, or maybe it's better to call it a theorem, but let's see what the statement is. Okay, maybe this is a proposition, but later I'm going to use this proposition to prove an important result. So if I give you the matrix of this form, it's companion of polynomial D1, companion of polynomial D2, and so on. And then I look at the matrix that they give me. And I look at so this is, let's say that this is a rational canonical form of this linear transformation T. We know that if I give you a linear transformation, you can always find a matrix representation for T that is of this form. And moreover, we have that as part of the definition of rational canonical form, kind of in the second part of the theorem that we proved, we have that the last one is going to be the minimal polynomial of this linear transformation. So here again, as part of definition of linear, as part of definition of being a rational canonical form, I'm assuming that D1 divides D sub 2, and they are monic polynomials, monic non-constant polynomials. So if this is a rational canonical form of the linear transformation T, then the minimal polynomial of T is the last one, the last polynomial, and the characteristic polynomial is the product of these sub i's. You see, in particular, I get two results. One of them is that when I evaluate the characteristic polynomial at T, I end up getting 0. We see this because this is a multiple of the minimal polynomial. This part of this proposition is called the Cayley-Hamilton theorem. Every polynomial, every characteristic polynomial of every linear transformation vanishes at that linear transformation. That's called the Cayley-Hamilton theorem. Alternatively, we can say that the minimal polynomial of any transformation divides its characteristic polynomial. Now we have it for free over here. The next thing that we see out of this is that every irreducible factor, so P is an irreducible factor of its minimal polynomial, if and only if it is an irreducible factor of its characteristic polynomial. This is also an important result, very important. Let's see why this is the case. So an irreducible factor of the minimal polynomial is precisely. So we have already, by Cayley-Hamilton, we know that the minimal polynomial divides the characteristic polynomial. So of course, every irreducible factor of this is going to be an irreducible factor of this one. But the converse is also true, because if I tell you that P is a minimal polynomial, is an irreducible factor of this one, then P is an irreducible factor of this product. It should be an irreducible factor of one of these, but all of them divide the last one, which is the minimal polynomial. So we get this part as well. But let me go through the argument a bit more slow. So we know that T, okay, so the assumption is that this is a rational canonical form of this. We have already proved that the last polynomial would be the minimal polynomial of this linear transformation. So this part we don't need to reprove again. Now, the characteristic polynomial of T would be the same as its as this matrix. And that means I need to understand what is determinant of xi minus this matrix, and that means this diagonal block form matrix. By the exercise, the determinant of this matrix is the product of determinants of these blocks. But determinant of xi minus this companion matrix is nothing but the characteristic polynomial of the companion matrix. So if we show that the companion matrix the characteristic polynomial of a companion matrix is the same as the polynomial that we started with, if we show this equality, then I can replace this one by d sub 1, the next one by d sub 2, and so on, and we get the equality that we were looking for. So we get that f sub t, the characteristic polynomial, is product of these d sub i's. Okay, so let's focus on the claim why we have this equality. I need to show that the determinant of xi minus the companion matrix is dx. We are going to proceed by induction on the degree of the polynomial. If the degree is 1, then the polynomial is simply x minus a, and that means that the companion matrix is just a 1 by 1, it's a number, it's simply minus a, and that implies that determinant of xi minus this companion is x minus a, so there is nothing to prove here. Now we proceed by induction step. We proceed to the induction step. I need to compute determinant of this matrix. X on the diagonals, negative ones off diagonals. So the last entry, however, here is x minus a sub m, x plus a sub m minus 1. So off diagonal, just below the diagonal, I have negative ones. On the diagonal, I have x's till I get to the last column, where I get a sub 0, a sub 1 dot x plus a sub m minus 1. So it seems that my screen is frozen. Let me stop sharing and then share again. Okay, so I need to compute determinant of this matrix, and what I will do is to use expansion with respect to maybe the first column. So that means what? That means I choose the first expansion with respect to the column, means we choose 1, 1 component and then delete the first row and the first column. Then I get x over here times negative 1 to some appropriate power, I will say it later, and determinant of the rest. So in general, when we exclude the ij entry, we have to take the ij entry, multiply it by the determinant of the rest, and then multiply it by negative 1 to power I plus j. In the 1, 1 entry, negative 1 to power 1 plus 1 is just 1. I need to multiply x by determinant of the rest. Now, determinant of the rest, how does it look like? It looks like a matrix of the same form. So x is on the diagonal except last one, where I get x plus a sub m minus 1, and then negative ones just below the diagonals, and the last column are going to be a1 dot, and the last one would be x plus a sub m minus 1. So I can use the strong induction hypothesis to write down that this determinant is nothing but the matrix, the polynomial that we get by looking at these a sub i's. So essentially this one. This matrix is nothing but the companion matrix of this polynomial, and therefore its determinant is this companion of the determinant of this companion matrix by the strong induction, by the induction hypothesis, is the same as this polynomial. So this term of expansion with respect to the first column is easy. We have already computed it is x times this polynomial. Now let's go to the next term in this expansion. The good thing is that in the first column there are only 2 non-zero terms. So this means that when I expand it with respect to the first column, I need to work out only 2 terms. Now, looking at this term, I have negative 1. I need to multiply whatever I get by negative 1. And then negative 1 raised to power 1 plus 2, that's an odd number. So that's a negative sign over here because of this. Now, determinant of the matrix that I get after I drop the first column and the second row. So I drop them out, I see what I get. I'm gonna get a matrix where the first row consists of 0, 0, 0, 0, 0 till I get to a sub 0. That's over here. The next one would be over here. And if you think about it, the first one would be -1, the next one would be x, and then zeros till I get to a sub 2. The next one, zeros over here, 0, -1, x, till I get to a sub 3. And I go like that. So 0, 0, 0, 0, 0. Here I need to write down x plus. I made this mistake several times. X plus, x plus, x plus. So in the last row, I get 0, 0, 0 till the one just before the last one is -1, and then the last one is x plus a sub n minus 1. But what is this one? In order to understand this time you are going to use the first row and expand it using the first row. And why the first row? Because in the first row we have only one non-zero term. That can help us. So I'm going to expand it with respect to the first row. That means I get a sub 0. Now I need to multiply this by -1 to power summation of the indices. The whole matrix is an m-1 by m-1 square matrix. This is the last entry of the first row. That means that's the 1, m-1 entry of this matrix. Therefore, I need to multiply it by -1 raised to power 1 plus m-1, because this is the 1, m-1 entry of this matrix. So the whole thing is supposed to be multiplied by determinant of the matrix that we get after I drop the first row and the last column. So I need to drop these things, and I ask myself, what is the matrix that I end up getting? So the first one, I get -1, then x, bunch of zeros. -1, x, bunch of zeros. Next one, I get 0, -1, x, bunch of zeros. 0, -1, x, bunch of zeros. As you can see, we end up getting an upper triangular matrix with -1s on the diagonal. So in general, again, as part of your exercise, similar to this, similar to the block form. In fact, we had already had it, but it's similar to that. This one is not diagonal, it's upper triangular. If I give you an upper triangular matrix, then its determinant is nothing but product of the entries on the diagonal. Therefore, determinant of this matrix is nothing but -1. How many -1s do I have? m-2 of them. So it would be -1 raised to power m-2. And we had already this multiplicative term, so -1 raised to power m. Okay, so it's only about parity. I can write down +1 or -1, doesn't matter. So +1, a sub 0, and then the whole thing gives us a sub 0. So this means that this determinant that we started with to understand, we expanded with respect to the first column. The first summand is this one, and the second summand is a sub 0. So altogether, we get that the characteristic polynomial of the companion matrix of the polynomial D is x times this plus a sub 0. And that's precisely D. So we get that the companion matrix of the polynomial D is D. So altogether, we get that the characteristic polynomial, we get that the characteristic polynomial of this linear transformation is product of D sub i's, and therefore, so let me so therefore we see that the characteristic polynomial is a multiple of the minimal polynomial, and so when I evaluate it at t, I get 0. That implies Cayley-Hamilton. And moreover, let me repeat the last part of the argument, that if p divides f sub t and p is irreducible, then p divides this product. Because it is irreducible, it should divide one of them. But every one of them divide the last one. And that's the minimal polynomial. So we deduce that every irreducible factor of the characteristic polynomial is an irreducible factor of the minimal polynomial. The converse is automatic because the minimal polynomial divides the characteristic polynomial. Let's stop at this point. We'll continue and see more applications of these results for now.